Artificial intelligence has rapidly evolved from a niche academic discipline into one of the most transformative technological fields of the modern era. Today, terms such as artificial intelligence, machine learning, deep learning, large language models, multimodal systems are frequently used interchangeably. However, from both a technical and research perspective, these concepts represent different stages in the evolution of intelligent systems. In this video, we will examine what artificial intelligence actually represents, how machine learning emerged within AI, while deep learning transformed modern AI research, and where current research directions are moving today. Rather than treating these topics as isolated buzzwords, we will look at them as part of a broader historical and scientific progression. To begin, let us first examine what artificial intelligence originally aimed to achieve. Artificial intelligence or AI is fundamentally concerned with building systems capable of exhibiting behaviors associated with intelligence. Historically, AI research mainly focused on these questions below, such as can machines reason? Can machines make decisions? Can machines represent knowledge? Can machines interact intelligently with the surrounding environments? Early AI systems were primarily symbolic and rule-based. Researchers manually encoded logical rules, knowledge representations, inference procedures, and decision frameworks. These all things were manually encoded earlier. And these systems performed well in constrained environments, particularly where explicit reasoning could be formally defined. However, symbolic AI encountered significant limitations. Real-world environments are uncertain, noisy, high-dimensional, and often impossible to model through manually engineered rules alone. As the complexity of problems increased, researchers began shifting toward systems capable of learning directly from the data. This transition led to the rise of the machine learning. In other words, however, as these symbolic systems encountered practical limitations, researchers gradually shifted toward data-driven approaches. This transition led to the emergence of machine learning. Machine learning emerged as a practical and statistical approach to artificial intelligence. Instead of explicitly programming every rule, machine learning systems learn patterns directly from examples and observations. At its core, machine learning attempts to approximate functions and discover statistical relationship within the data. This shift was extremely important because it allowed systems to generalize beyond handcrafted logic. Machine learning is commonly divided into several paradigms, such as supervised learning, unsupervised learning, and reinforcement learning. Under supervised learning, models learn mappings between inputs and labeled outputs, and their applications include classification, regression, recommendation systems, and predictive analytics. Under unsupervised learning, systems attempt to identify structure within unlabeled data, and their examples include clustering, dimensionality reduction, and representation discovery. And under reinforcement learning, agents learn through interaction with environments using data-driven and reward-driven optimization techniques. And their applications include robotics, autonomous systems, and strategic decision making. Traditional machine learning introduced highly influential algorithms such as support vector machines, decision trees, random forest, gradient boosting methods. These methods were powerful, but they often depended heavily on manual feature engineering. Researchers still needed to design informative and representational data for the model. This limitation became one of the major motivations behind the emergence of deep learning. In other words, while machine learning achieved significant progress, many traditional approaches still depended heavily on manually engineered features. Deep learning emerged largely as a response to this limitation. Deep learning can be understood as a subset of machine learning focused on hierarchical representation learning through neural networks. Instead of relying primarily on handcrafted features, deep learning systems learn representations automatically from the data. This capability dramatically changed fields such as computer vision, natural language processing, speech recognition, generative modeling, and multimodal models and reasoning. The availability of large-scale datasets, high-performance GPUs, and improved optimization techniques accelerated progress significantly. CNN, convolutional neural networks, transformed computer vision. RNN, recurrent neural networks, advanced sequential modeling. However, one of the most important developments in modern AI research was the introduction of the transformer architecture. Transformers fundamentally changed how models process sequential information through attention mechanisms. This architecture became the foundation for modern large language models, generative AI systems, multimodal models, and large-scale foundation models. Today, deep learning represents the dominant paradigm in many areas of AI research, yet despite its success, important limitations remain. In other words, despite the remarkable success of deep learning systems, important challenges remain unresolved. Modern AI systems are extraordinarily capable, but they are far from complete forms of intelligence. Current challenges include reasoning limitations, hallucinations in language models, interpretability problems, data inefficiencies, robustness issues, and high computational cost. Large models can generate impressive outputs, yet they often struggle with casual reasoning, long-term planning, symbolic manipulation, and grounded understanding. These limitations are now shaping many active research directions. Understanding these weaknesses is important because research progress often emerges from identifying where current systems fail. In other words, these limitations are now shaping several major AI directions and research forms in the modern AI. Modern AI research is increasingly moving towards systems that are more general, more efficient, more interpretable, and more capable of reasoning across modalities and environments. Several important directions include large language models and foundation models, general purpose models capable of adaptation across tasks, multimodal AI, systems that integrate language, vision, audio, and structured information, neuro-symbolic AI, attempts to combine neural learning and symbolic reasoning and logical structure, efficient and sustainable AI, research focused on reducing training costs, energy consumption, and inference complexity, AI alignment and the safety, ensuring that increasingly powerful systems remain reliable, safe, and aligned with human objectives. These research directions indicate that modern AI is evolving beyond pattern recognition toward broader forms of reasoning and interaction. In other words, taken together, these developments illustrate the broader scientific evolution of intelligent systems. In conclusion, artificial intelligence, machine learning, and deep learning should not be viewed as interchangeable concepts. They represent different stages in the scientific evolution of intelligent systems. Artificial intelligence defines the broader objective. Machine learning introduced statistical learning from the data, and deep learning enabled large-scale representational learning and transformed modern AI research. Understanding this progression is important not only for learning AI, but also for understanding where future research opportunities may emerge. In upcoming videos, we will further explore neural networks, transformer architecture, research papers, reproducibility studies, and modern AI systems from a research-oriented perspective. Thank you so much for your time and for exploring this frontier with me today. I know AI research can get dense, so I truly appreciate you sticking around to the end. If you enjoyed this, hit that subscribe button and I will see you in the next video. Thank you.